Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, my name is Nabil Naja, an information systems student with a student ID 2024-2024. And today, I would like to present my practical report on the machine learning course, which in today's assignment, I focus on developing an intelligent computing or machine learning solutions for banking fraud detection. So let's begin with the core form, which is the data loading and initial exploration. In this first step, I set up the foundation of our programming environment, which is I imported the Python libraries. I utilized pandas uh, for handling data sets, NumPy for high performance numerical operations, and also Matplotlib alongside the Seaburn to build our visual characters. Furthermore, I use specific sklearn models that were integrated to handle data processing, model building, and evaluation metrics. Alright, once the libraries were active, I loaded the raw dataset named banking transaction.csv, and then to fully comprehend the dataset's characteristics, I use the dataset or use the df info command, and then I the output revealed a massive enterprise scale dataset containing exactly 10,000 entries with the 10,000 entries and 20 columns, distinct feature columns. Looking at the structural composition, the dataset consists of 1,000,005 floating points, 12 integers, and 2 categorical object strings. And then, finally, I called the tfhat command to verify that our features such as transaction amount and device risk scores were accurately read into the system. Moving into the part two, which is exploratory data analysis or EDA, which is essential to study the underlying distributions and relationship within the data visually before we rush in, before we rushing into training our machine learning data model. And then in here, I generated two critical plots side by side to guide our modeling strategy. The first visualization on the left is the target variable distribution plot by plotting the frequencies of our level frog like and we can observe a severe cost imbalance. The legitimate transaction labeled as false dominate the dataset with roughly 95,000 entries, while the preference transaction labeled as a true from a tiny minority of about below 2,000 entries. This highly skewed distribution reflects a real-world banking environment exactly, where fraud acts as a rare anomaly. The second visualization on the right is the feature correlation heat map. This matrix measures the strength of linear relationship between our continuous numerical attributes, such as login attempts, transaction amounts, and device trace score. Interestingly, the matrix is heavily populated by very large sets of blue and white, yielding correlation values that hover closely around zero. This specific findings is incredibly vital for our task. Why? Because the fundamental assumption of our naive Bayes algorithm is class conditional independence, meaning it assumes that features do not influence or correlate with each other. Because our features show virtually no linear correlation, our dataset perfectly fits the theoretical criteria of naive Bayes, ensuring that our model probability estimates will remain objective and unbiased. So next, let's examine the pre-processing pipeline in part 3. The router is rarely ready for direct mathematical computation, so this pipeline was constructed to clean encoded state and scale our attributes. First, I programmatically verified the presence of empty cells using the df_is_no.sum command. As expected from our initial inspection, the output confirmed exactly zero missing volume right here across all columns, right? Meaning no row indentation or drop measures were recorded. And then second, I dropped the transaction.id column from a data science perspective. Unique identifier series causes no statistical correlation with fraud patterns. Removing it prevents the model from capturing meaningless noise and reduces computational overhead. Third, because machine learning algorithms rely heavily on vector mathematics, they cannot interpret raw text strings. Therefore, I implemented label encoder to transform categorical features like payment channel and authentication path into uniform numerical representations. Fourth, I separated our independent features into matrix X and the dependent target fraud flags into vector Y using the trend test function with a standard 80-20 ratio and the random state of 42 for reproducibility. The data was built before Kata. This generated a training set of uh, 8,000 rows to let the model let fraud behavior the testing set of 2,000 rows kept completely hidden to validate model performance. And finally, I applied the standard scalar to standardize our continuous numerical data. To scale our attributes to have a mean of 0 and a variance of 1. This step is indispensable because Gaussian naive bias assumes a normal bell curve distribution. Tenscaling or scaling ensures that massive scales like Monley balance do not numerically drown out smaller scales like login effects. Alright, this brings us to the PowerPoint, which is the model for modern training. According to the structural guideline of this assignment, because the last digit of my student identification number or my name in Indonesia ends in an even number, namely 044, I am required to implement the net bias algorithm. Given that our features consist predominantly of continuous financial figures and scaled digital behavior, I specifically selected the Gaussian bias variant represented in scikit-learn as Gaussian NB command in here. The construction process was straightforward yet powerful. I initialized the algorithm into an object named model MD, and then invoked the code training method with command, passing our scaled training features, extreme scales, and along with the ground truth historical labels white train. During this execution phase, the algorithm maps out the mathematical boundaries of fraud. It computes and saves the precise mathematical means and variance of every feature for both distinct classes, the non-fraud class and the fraud class. The successful controls of the shown in the report confirms that all model parameters were successfully instantiated and the learning phase character, the learning phase across all the 8,000 training observations concluded flawlessly without any execution at all. To test how robustly our model can generalize to unseen real-world data, I passed the 2,000 instances of our hidden testing partitions through the train classifier using the predict command, saving the output word print. We, uh, when we analyze the generate classification report, the mathematical performance is truly spectacular. The global classification accuracy reached the global classification the accuracy model is 95.4%. Looking closer at the class specific metrics, the failures proposition require an F1 score for both the safe class and the full class achieve a flawless score of 1. This implies that the model achieved perfect precision, meaning it almost perfect precision, meaning it did not mistake any legitimate transaction for fraud, and perfect recall, meaning it successfully caught every single thread to cross-verify this outcome and rules out any logical flaws. I visualize the confusion matrix heat map. The diagonal boxes from the top left to bottom right represent our correct classification. Right, this visualization provides definitive graphical proof that our Gaussian bias classifier achieves absolute precision in separating legitimate banking activities from fraudulent actions within this test dataset. Alright, and that concludes my practical report session today. And thank you for your time.